Hello, everyone. It's my pleasure to invite Professor Andre Ferron from Caltech. He's the William L. Valentine Professor of Applied Physics and Electrical Engineering. He earned his BS degree from Caltech, MS and PhD from Stanford, and he also worked at Hewlett Packard from 2009 to 2012, and he primarily worked there in seminal quantum optics and also nanophotonic devices. At Caltech, he has been working on nanophotonic technologies, both in the classical as well as quantum applications. That includes optically addressable quantum bits, optical quantum memories, microwave to optical quantum transduction, metasurfaces, metamaterials, both for multifunctional imaging applications. And he's the recipient of the 2018 Adolf Lomb Medal of Optics that recognizes a noteworthy contribution to optics made by a researcher who is still early in his career. It's a. And then welcome Andre, and Andre is going to give a talk on 3D meta-optics for sorting light by wavelength, polarization, and angle of incidence. Welcome, Andre. The stage is yours.
Thank you. Thank you very much for the invitation, and thank you very much for the very nice introduction. So Ajay already mentioned, I work on several different topics all related to optics. Part of my group works on quantum photonic technologies, and I'm going to have one slide about this work. And most of my talk will be on my classical nanophotonic technologies work. And specifically, I was going to talk about meta optics, basically meta surfaces, meta materials for sorting light by all its degree of freedom, explicitly wavelength, polarization, and angle of incidence. So as I promised, I will start with an overview slide of our work on quantum networking. So this is what about half of my group is doing. So in this context, what we are interested in is connectivity between different quantum systems. For example, let's say you have a quantum computer, like a superconducting quantum computer. These devices operate at millikelvin temperature, and you can think of them as having superconducting quantum bits interacting with photons that have a frequency of a few gigahertz. Now, if you want to interconnect this quantum computer with another quantum computer of the same kind, and if you want to do this at reasonably long distances, what you need to do is to use some photonic link such that you can transmit quantum states even at room temperature. So now the main challenge is, how do you actually take quanta that live at a few tenths of a millikelvin and transport them to a different system via room temperature link. And for this, we actually need to have a device which is called a transducer that takes a single microwave photon at gigahertz frequencies and converts it into a single optical photon. And this optical photon can travel via an optical fiber link, and you can have a very similar setup at the other end of the network. Now, if this optical fiber link is short, you can just use one fiber, and by short, I mean on the order of, let's say, 10 kilometers. However, if you want to do longer networks, what you need to do is to actually break this fiber into multiple segments, and these segments are linked by what is called quantum repeater nodes. These are small quantum machines, and their only role is to actually establish entanglement between this and the end of this segments. And in my group, we work at various technologies that hopefully one day we will find them at all these stations, either the quantum repeater node or the transducers. For example, these are some devices that we work on for applications on quantum repeater nodes. These are photonic crystal devices that are fabricated in this material called yttrium orthovanadate that is doped with various lanthanides, we are mostly working with the ytterbium 171 atoms, lanthanide atoms that are doped in these structures. At the transducer link, you may find devices that look like this. So these are some devices we are developing that are composed of microwave, superconducting microwave resonators, and that are sitting on a substrate that is also doped with ytterbium 171 in yttrium orthovanadate. And these devices, their role is to mediate transduction between single microwave photons and single optical photons. And this transduction is mediated via these atomic transitions that provide a very high effective second order nonlinearity. So this is an overview of our quantum networking work. Next, I will move to the main topic of today, which is on classical nanophotonics. And I will start by an introduction of some of the work that we've been doing for the past decade on flat optics. So this is the area of optical metasurfaces that has been around for about 15 or more years. And here the idea is that you want to make various optical components like lenses, wave plates, polarizers, and these wave plates are usually done via bulky pieces of glass or various crystals, and you like to make them using nanopatterned surfaces. And now if you think of a surface that is patterned at nanoscale, and I should say that doesn't have to be nano, but the relevant dimension is the wavelength. So let's call it sub-wavelength scale. So if you have a surface which is patterned at a sub-wavelength scale, what you like to do is to engineer the emerging optical wavefront. So let's say you have a plane wave that is incident on this structure. What you like is to shape the emerging optical wavefront with a spatial resolution on the order of one wavelength. And our group has developed a lot of technologies to do this task. These are some pictures of some optical metasurfaces that we made using amorphous silicon nanopillars. These are nanopillars with elliptical cross section that have about half a wavelength in height. And their role is to control the wavefronts with this sub-wavelength, the sub-wavelength spatial resolution and high transmission. Now, I should say that there is a very large community of people working on metasurfaces. These are some examples of metasurfaces developed via various technologies, including titanium dioxide nanopost, other materials like silicon nitride, silicon, plasmonic devices. So as you see, like this, all these papers are about 10 years old or older. So this is like a booming field, and there is many groups working in this area right now. So it's impossible to cite everyone. Now, why is this technology important? One reason is that it allows for vertical integration of optical components. So if you think of a microscope objective or let's say a camera lens, it is generally constructed by having multiple lenses that are sitting on top of each other, and these lenses have are very well polished, have like very specific geometrical shapes. Generally, is a bit of an art to design such a system, and it's also very difficult to assemble and put together. You need to do this very careful polishing, and then you have to mount everything together with very good tolerance. But with metasurfaces, what you can imagine is that you can pattern metasurfaces on various substrates with very well-defined thickness, and each metasurface basically provides a very specific mathematical transformation of the optical wavefront, and this way you can simply make all these devices on top of each other in a multi-layer lithography type setup. Now, the other reason why this is important is because you can imagine vertical integration with electronics. Now, image sensors and lenses are generally fabricated via different technologies, and you put them on top of each other. But now with metasurfaces, you can imagine having an image sensor, and then directly on top of it, you can stack multiple layer of metasurface optics, eventually maybe even the same type of production line. Another thing, the reason why I think this is interesting is because it is related to the field of conformal optics. So, for example, if you have some object that has some arbitrary shape that is defined by some functionality that this object might have. So if you have light that is propagating through this object, the optical wavefront will be distorted. But let's say that you want this object whose functionality is shape is defined by something else. You want to perform a certain function, like for example, focus light. You can think of patterning a metasurface on it that is linked or correlated to the shape of this object, and you can transform the optical wavefront such that light is focused. So this is just an example, but it can be you can have whatever functionality you would like. And to develop this functionalities or technologies, our group has looked at various metasurface platforms. So one of the most used one is based on silicon nanopost. For example, if you imagine a lattice of silicon nanopods. In this case, it's a hexagonal lattice, and the spacing is on the order of half a wavelength. Height is almost like one wavelength in air. And now, if you simply take this silicon nanopost and you look at the phase response of this device as you change the diameter of the nanopost from lambda over 8 to lambda over 3, you'll see that the phase varies quite smoothly from 0 to pi, while the transmission is quite high, 90% or higher. There are some resonances here, but actually they can be avoided and when designing a device. So basically what this does, it allows you to have very good spatial control of the phase. Actually, although the simulation is done for a full lattice, it works very well that you can approximate each nanopillar as an antenna, and each nanopillar basically imposes the phase shift that is defined by this relationship. So you can do one-to-one phase map almost between like the phase of the light and the diameter of this nanopillar. So this technology allows you to achieve phase-only control and allows you to have the freedom to design any elements to control optical wavefronts. Now, one thing that you can design, one of the most simplest thing is polarization in sensitive lens. For example, a lens basically changes a plane wave to a spherical wave. So you want to do this, you have to design this spherical wavefront. Generally, we don't have the capability to apply very large phase delays. Most often, you see a phase delay from roughly 0 to pi. So to design devices that have like a relatively large diameter, what you need to do is to break this phase profile into multiple Fresnel zones. This is how the profile ends up looking like. And if you match this profile to the diameter of nanopillars, you end up with this type of structure for nanopillars. And if you do a simulation, basically you'll see that if you send a plane wave, a light is going to get focused very nicely into diffraction limited spot. Now, taking this further, one of my group's contribution to this field was to show that actually you can not only generate just phase profiles, but you can achieve complete phase and polarization control with high transmission. So what do I mean? I mean, let's say that you have the metasurface object, and this is the side view. So you have, let's say, light that is polarized along X. And as it moves through this object, you can imagine that this object is divided in pixels, and each pixel, its role is actually to change the light as it propagates through it. So as the light propagates through each pixel, it acquires a phase delay and a polarization transformation. And here by polarization transformation, I mean that let's say you start with linearly polarized light at input, you can have arbitrary circular or elliptical polarization at the output. So and this way you can generate arbitrary phase and polarization maps. And the phase is defined with respect to the x component of the electric field. And we have shown that you can do this with asymmetric pillars. So for example, you can think of having elliptical nanoposts, and by changing the diameters and the orientation of this nanopost, you can achieve this complete phase and polarization control, and it's with high efficiency, generally greater than 90%, and the sub-wavelength pixel size. Now we apply this technology to various type of let's say more specific applications. One of the most advanced one that we've done was to show that you can make spectrometers and multispectral analyzers. Now, if you think, for example, of a spectrometer, it's generally formed by you have a light source and that carries some spectral information from a sample. It goes through a slit, then it's incident on a focusing mirror. The focusing mirror is focusing or is collimating the light on this grating. The grating disperses the light, and there is another focusing mirror that focuses light to this detector array. So this is what you have in most tabletop spectrometers. And we wanted to see if it's possible to apply metasurface technology to take this relatively sophisticated instrument and make it much more compact. And for this, we use the concept of folded optics. So if you think of a compact device, can you make it actually in a piece of glass? So for example, if you imagine a piece of glass that has simply like some rectangular cross section, you can imagine that light can go in this piece of glass, can bounce back and forth between these two surfaces. And as it hits various of the areas of this surfaces, it can be incident on various metasurface components like lenses, beam splitters, and so on. And it comes out and it's processed in a certain way. And this is how our spectrometer works with this concept. So you have a glass slide, and this is about 1 millimeter thick and a couple of millimeters long. Light comes in, so you can look at this blue arrows. It comes in from this end through an aperture. Then it hits first a grating, and then different wavelengths of light are going to be dispersed by these gratings. And then our goal is to make sure that this dispersed light comes out at this focal plane, and it's very nicely focused, and it is nicely dispersed. So in order to do this, we are using two metasurface focusing mirrors, and these focusing mirrors have this type of phase profile. You see something which is not trivial. Also, they are designed to work in two polarizations. They are designed to work at an angle. So there is a lot of metasurface design that goes into making this device work. But light bounces back and forth and hits these two metasurface mirrors, and then bounces back and forth a few times, and then it comes out at this focal plane. And so there is an aperture here, and also there's aperture at the input, and there is gold that is used as mirror in order to keep the light inside the slide. And these are just some data showing that actually as light comes at this end, it's very nicely focused. It operates between 760 and 860 nanometer with a resolution of about 1 nanometer. These are some pictures of the fabricated devices on a chip. Actually, you can make a lot of them. Here you can see the grating and the two other metal surfaces, and then here is one of the apertures. And these are some images of how the metal surfaces look like. So when you fabricate this, we start the glass slide. There's amorphous silicon. We etch pillars in this amorphous silicon. Then we coat everything with some SU8 and with gold. And we have the input and output apertures. As I said, this works very well both for T and TM light with the efficiency on the order of 25%, which is actually quite good given the fact that actually you're having so many reflections back and forth between those two gold surfaces, and this is the measured resolution as expected around 1.2 nanometers. Now you can take this concept even further, and you can make a imaging spectrometer. Spectrometers map just the wavelength, so it's a unidimensional space. But generally, when you use the 2D image sensors at the output, there is the two dimensions that could be used. So what you can think of is you can map in one direction, you can map the wavelength, and the other direction, for example, you can map the incident angle of the light. And this is very similar to what is called like a translation type hyperspectral analyzer, where let's say from on one wavelength, on one direction you can do imaging, and the other direction you can do the spectrum. And for this, we actually design more sophisticated devices where we have 4 meta surfaces on one side, and again works from 750 to 850 nanometers. And this is how light is mapped. So it works from minus 15 to 15 degrees angles, and different wavelengths are going to be mapped differently on the image sensor. And resolution about 1.5 nanometers, 0.1 degree angular resolution. This is how the meta surfaces look like. And if you measure the device, this is how the image on the sensor looks like. This is the mapping that we have. And to probe this device, we made some special samples. So basically, it's a meta surface that projects a Caltech logo, and for different wavelengths, there is a minimum of transmission in this Caltech logo that basically gets scans from bottom to top. So this is what we expect to see, and this is what we measure. So just showing that this is a nicely working device. So these are arguably some of the most compact spectrometers that what one can make, and actually show beautifully the power of this technology. Now, if you think, take a step back and I think about flat optics. So what are the opportunities? So here we can make this custom phase polarization amplitude mask. You can also think about tuning the devices. But I think one of the most interesting one is multifunctionality. So can you have meta surfaces that can blend multiple functions into the same device? These are some type of functions that you may wish for your device. So you can have spectral control, waveform control, polarization control, and so on. So I already showed you some example of spectral control and wavefront control. So besides the work that I showed you before, we have done other work towards this multifunctionality. For example, using these phase masks that control both phase and polarization. If you can have an incident wavefront, you can design a different phase mask for X polarized and Y polarized light, and so the light will be focused to different distinct points, and this is what we see in simulation and measurement. So this is equivalent maybe to 2 Laston prisms and 2 lenses. So it combines the functionality of these 3 devices. So again, this is polarization phase multiplexing. You can think of doing angular multiplexing, so you can design the metasurface that's to have a different response for different angles of incidence. And for example, you can project different holograms in far field. It can be, for example, either a Caltech logo or this LMI logo. Before the efficiency was about now 90%. Here you can see that we're taking a hit in efficiency. It's about 50%. We also can do spectral multiplexing. So this is something that is particularly well suited for metasurfaces. So you can design different phase maps for different wavelengths. Actually, in this case, what we wanted to do is to design metasurfaces such that different wavelengths are actually focused at the same point to compensate for the chromatic dispersion of inherently thin metasurface devices. This is something that comes for free in a refractive lens, but actually to have a metasurface lens focus different wavelengths to the same point, actually you have to do some work. And in this case, actually what we did, we show lenses that focus both 1550 and 915 nanometer to the same point. And again, we do take a hit in efficiency when we do this. So as you can see, you can think of doing various kinds of multiplexing with this two-dimensional structure. And I think there is a very interesting fundamental question about how well can we do using these two-dimensional structures. What is the limit and what happens if we go to 3 dimensions? So if you want to tackle these questions, you have to think at metasurfaces as discrete objects composed of multiple scatterers. So in this case, I show a two-dimensional arrangement of, let's say, nanoblocks or sub-wavelength blocks made of some high refractive index material. And you can imagine having different colors of light, different polarization that are mapped with different transformation as the light goes through. Now, how many ways can you control the output? So at the end of the day, if you have a single metasurface, you are limited by the number of, let's say, building blocks in this metasurface. But you can think of stacking multiple metasurfaces on top of each other, and this will increase the number of degrees of freedom. Or you can think of like a fully 3D engineered optical material where you have like a three-dimensional collection of scatterers of sub-wavelength blocks that fill the space, and this is a highly scattering medium. And I think it's very interesting to ask the questions: what can you do with such a medium? How many ways can you actually control the light at the output? Can you do something useful that is very difficult or maybe impossible to do in other ways using like a single layer metasurface or a refractive optical device? And towards this end, about 7 or 8 years ago, we started to think about this problem of color splitting on image sensors. So if you have a color image sensor, RGB, so this is something that creates color images for our eyes to see. They're divided into pixels, and each pixel, each set of 4 pixels for what is called the Bayer pattern. In these 4 pixels, you have 2 green filters, 1 red and 1 blue. And inherently, these pixels are limited by some absorption efficiency in the material that does this filtering, which is about 30%. So we wanted to see, can you actually make better than that limit of 30%? Can you improve the throughput? And also, can you maybe design filters that are more sophisticated? There can be of different wavelengths, or can have very distinct spectral profiles. And so the idea is that instead of having this absorptive filters, you have like a block of, let's say, engineered three-dimensional material that acts as a scattering medium. So it takes white light in and splits it into these pixels by different wavelengths and polarizations. And it doesn't even have to be like a 2 by 2 array. For example, here I show a 3 by 3 array. And to navigate in this space, we use a lot of inverse design because it's very difficult to rationally design a structure that does this kind of wavefront control. So in the field of inverse design, we've been learning from the groups of Ilya Blonovich, Owen Miller, and Elena Vukovic. They have designed a lot of two-dimensional structures. We are applying these concepts in 3 dimensions. And so what we have is a 3-dimensional design region. It's a cube about 4 wavelengths on its side. And what it does, it takes white light and it splits it into 4 different wavelengths. So you have red, green, and blue wavelengths. For green, actually, you are splitting X polarization and Y polarization. We're using 2 materials, titanium dioxide and silicon dioxide. We are limiting this region to, let's say, have 5 layers. So each layer is 400 nanometers thick. And we had a minimum feature size of about 60 nanometers, which we thought it's somewhat reasonable to fabricate. So we are looking at these cubes that do this splitting, and you can optimize it. And if you look at the performance, indeed, you see that you can actually get pretty good splitting. So with the efficiency more than 30%. And for this middle spectral band for green, indeed, you see that the one polarization is sorted with respect to the other. And one question you may ask is, does it matter that I have so many layers? It's 5 layers. So can I get this with a single meta surface? And the answer is that you do need this many layers. Basically, as you increase the number of layers, the efficiency is going up. The polarization contrast and color contrast does go up. And I should say that other groups have done similar work in the field, work from Shanhui Fan, where actually they have discretized the volume much more. So they have pixels that are 40 nanometers by 10 by 10 nanometers, also with silica and titanium dioxide, and they can push this efficiency almost up to 100%. There's also work that has been done just with like more like meta surface type structure, and they achieve some level of splitting. But as I said, it's quite difficult to get very high efficiencies in with a single layer. And this is another single layer type spectral router. Now, to fabricate these structures, we first looked into millimeter waves. So the 30 gigahertz. So we fabricated these devices that are composed of multiple layers of polypropylene. And this is something that actually you can hold in your hand. And we tested this device at the Jet Propulsion Laboratory. And these are some measurement results. So this is simulation showing that we expect this splitting of the spectral bands. Again, we are working between 7 and 12 millimeters, and you can imagine that we have 3 spectral bands that we label red, green, and blue. And here we expect to see that vertical polarization green goes in the lower left, and horizontal in the upper right. And this is experimental data showing that is what we see, and it's easier to see in these 2-dimensional plots that actually get pretty good spectral splitting. Now, my former student, Dr. Kaimur Balu, who worked on these devices, took this technology to JPL, and he applies it to these spectral bands of about 500 to 650 gigahertz. And here he uses silicon devices, and it's made out of a couple of layers of silicon, about 160 nanometers total thickness. And here he can get very nice spectral splitting. You can can have 4-layer devices or 8-layer devices. And here you can, let's see. Okay, now it's working. So you can see that the frequency is changed. Basically, this focal point moves between this three pixels, so you can get very nice discretization, the resolution for the wavelength. And this is measurement data showing that these devices actually work very well. Now, moving towards optics, my group has been working quite a bit in mid-infrared. Again, it's a bit easier to fabricate in mid-infrared because the dimensions are larger. And in this case, we are using two-photon polymerization printing using commercial tool called nanoscribe. And here the idea is that you focus the laser beam in a resist, and by two-photon polymerization, you get pretty high resolution, so you can fabricate with a resolution smaller than 1 micron, which is sufficient to make devices with sub-wavelength resolution, spatial resolution in mid-infrared. And this is an interesting band for gas identification and biomedical species identification. Now, so this resist that is used for this 3D printing actually has a nice transparency window between 3.5 and 5.5 microns. I should note that other groups have also experimented with this in the context of multilayer gratings. This is our structure, so we are making this again, this cubes. This is how the 3D printed structure looks like, and when we test it, again, we send laser light at different wavelengths, and we expect like different spectral bands to be split into this four pixels. We're looking again 3.5 to 5.5, and here you can see how the spectral bands are split by this structure. And as you change the wavelength from 3.5 to 5.5, we expect this spectral this focal point to move from the upper right to lower left, while moving through also to the upper left quadrant. And here you can see clearly that this is also what happens experimentally. The structures, the performance is not as good in experimental simulation as it's always the case, but we're getting still fairly good efficiency on the order like 40-50%. One tricky thing is that actually troubleshooting these devices in 3D is not the easiest thing to do for an academic group. Another thing that we looked is on sensor polarimetry. So the most compact way to do polarimetry is to look at incident light and split it into 4 Stokes vector that are maximally separated on the Bloch sphere. So you are splitting in circular polarization and 3 elliptical polarization. This is also something that has been demonstrated in a bigger setup with the meta surfaces. Here you want to do this everything on the pixel level. So this is how the device works. So it looks like the one that we fabricated, and this is what you expect in simulation in an experiment. So here, actually, because this is a non-orthogonal basis, all pixels are lighting up, and this is we observe a very good correlation between simulation and experiment. Now. With these devices are just splitting wavelengths and polarization. So I wanted to, can you actually imagine even more complex devices? So can you have devices that can split both wavelength polarization and the angle of incidence? And this is something that we have done only in simulation. For example, you can imagine a three-dimensional structure. Again, this is made out of much more layers, so it's actually 20 layers, each one 200 nanometers thick, which feature size of 60 nanometers. This is operating in invisible. So what this structure does, it is designed to scatter light in a very specific way, depending on the wavelength, polarization, and angle of incidence. So there are 2 pixels that are designed to respond to the wavelength. So this pixel should light up when you have green light, this pixel for red light. of polarization, XZ and YZ. They have these two other pixels, and for the angle pixels are these five that respond to the angular component of the light. So for example, if you see a pattern like this you have this pixel means it's red. This pixel means that light comes from 5 degree, 90 degrees. This pixel lights up, it means that your polarization is XZ. So you have different permutation of pixels that light up. Efficiency-wise, this works pretty well. So these are the 3 pixels that should light up, and generally you get about 50% of the light going into the right place. One thing that you may want to look at is what happens if you if you operate this device at parameters that you haven't designed for. For example, what happens if you change the polarization, but you rotate it from XZ to YZ? So in this case, you have this configuration. So this is 532 wavelengths. So this is normal incidence. This is XZ polarization. So as you rotate the polarization, you simply see that light is migrating from this quadrant to this pixel to this pixel. This may be expected because this is a nice polarization, is nice orthogonal basis. Now, what happens to wavelength? What happens if you switch from green to red continuously? So again, in this configuration, you see green light, normal incidence, XZ polarization. So as you change the wavelength from green to red, you see that light slowly migrates from this pixel to this pixel, while the other pattern remains roughly the same. And now with angle of incidence, again, green, XZ polarization, this is normal incidence. But as you change theta and phi, in this case, you see that the wavelength and polarization pixels stay roughly the same, while the other pixels have a different permutation of how they light up. But the conclusion here is that this acts as a very scattering medium. So even if you the very high scattering medium. So even if you operate the device in between the parameters that you design for, by looking at the response of this device, you should be able to figure out and backtrack what is the incident wavefront. So so given like say a laser beam or a plane wave with a specific wavelength, polarization, and direction within this parameter space, by looking at how the pixels light up, we should be able to identify it. And now, another thing that is interesting is what happens if you shuffle the pixels. So this device, this is the original device, and you can you can say that it was designed such that normal incidence comes in the middle and the other pixels are shifted in the same way as a lens would do. Now you can quantify this device by looking at the pixel response by averaging on the other degree of freedom. For example, if you look at the green pixel, this should not be sensitive to angle. And this is the angular plot, and indeed you see like the green pixel is roughly insensitive to angle. Same with the red pixels, same with the polarization pixels. The other pixels which are angular, if you plot the response in this angular coordinates, you see some angular response. So now you can optimize a different device that has the pixels shuffled, and you quantify this response, and you see that indeed some of these pixels that are angular sensitive, they show the angular sensitivity while the others don't. And then you can unscramble these pixels. Unscrambling means you just like in PowerPoint, you rearrange the pixels in the original configuration. And if you compare them, they actually look very, very similar, which means that this device actually doesn't really have a memory effect. So this acts as a highly scattering medium that is really doing what it's supposed to do without really remembering the angle of incidence of the incidence wave. Now, about fabricating these devices that I showed you at the beginning, that we can use nanoscribe or 3D printing to do devices in the mid-infrared, but you can imagine using multi-layer lithography. These are some devices that we've done in the context of meta surfaces, where you can stack multiple meta surfaces on top of each other. This is how they look like. So if you want, you can stack multiple meta surfaces by multi-layer lithography and alignment. You can also imagine maybe using something like a CMOS process. The CMOS process is basically consists of multiple wires, multiple copper wires that are in a very large that is stacked into a relatively large stack, about nine layers. You can imagine taking these wires and constructing a photonic structure and then etching away the wires. This is something that we experimented with. So it is one avenue, and then you can backfill with another material, or you can let the voids be. Also, you can think of maybe going to some more extreme structures. For example, there is this field of like three-dimensional nanoassembly, where you can use the DNA origami to that self-assembles in certain ways. So people have shown that you can do 2D patterns of DNA origami, and you can attach various nanobeads to it, either plasmonic or dielectric. And you can definitely imagine doing this in three dimensions. Uh, so these are some directions that we are excited about. So in conclusion, I would say that meta surfaces can be used for a variety of sophisticated applications, require control and light in very small form factors. I think is a relatively mature technologies, and there are a couple of startups and big companies that are already commercializing these technologies. In terms of this three-dimensional space, I think is a very interesting space. I think is the ultimate, say, design space for an optical engineer. We only explored binary structures, but I mean, if you can think that, I don't know, maybe 100 years from now, we'll have the capability to make three-dimensional structures that have multiple material, they have gain, they have loss. So it's a very big landscape of parameters, and I think it's a very interesting design space that can open some opportunities that are not easily accessible using conventional optical techniques. So this, I'd like to thank my research group and the previous research group members, and some of our collaborators, and also our funding sources. I would like to thank you for your attention, and I hope we have time for a few questions.
Yeah, thank you, Andre. Great presentation. Very cool results. Very interesting lithographic schemes that you have shown.
Thank you. Thank you.
Let me wait for. I mean, is there any questions from the? Any questions? Please raise your hand, and you can come to the mic, and you can ask the question if you have a question, or you can put those questions in the chat Q&A session. Okay. I have a question, Andre, and this is really interesting about this potential two-photon lithography that you're showing. But the dimensions that you have shown is of the order of micron scale dimensions. So essentially for photonic crystals or things like that is probably useful, I guess. So there are two types of scaling. How scalable this is, this scheme that you have shown from a manufacturable perspective. So yeah.
Well, I would say that this three-dimensional lithography technique that we are using, it's not very scalable in the sense that it's as scalable as maybe like as electron beam lithography, because basically you are using a scanning beam that needs to scan in three dimension and do the pattern. So it's not like a very high throughput technique similar to maybe photolithography. So I think it's not as scalable as we might want it to be. So it's going to likely be used more in specialized devices. But I think if you really want to make them, you can make them. Uh, However, I think this multi-layer lithography is just an engineering challenge. So I think if you have a application that you are going for, you have a very good design, and if you want to invest resources into a three-dimensional optical structure at a nanoscale, a sub-wavelength scale, I don't think it's an impossible problem. I say in CMOS electronics, the people are already doing that. It's just they are doing it in the context of designing a three-dimensional network of wires. So here it will be a different type of structure. It's not easy. It's probably expensive, but yes, it can be done. I see there are a couple of questions in the Q&A.
Oh, there are a few questions that have come up. Yes. Oh, Dr. C.Y. Sung from Raytheon, he's asking a question. Could you please comment on the reconfigurability on 3D meta devices?
I guess, I mean, I think that you can think of ways to reconfigure them, and it's not something that we have done. But for example, you can maybe think of having like a porous structure, and you can um, infiltrate it with liquids of different refractive index. That's what we can do. Or you can think of like maybe having some micro electromechanical structures that actuate maybe a few layers in that structure, bring them then closer to each other, thus changing the response. Uh, Generally, for these structures, you need to have a relatively high change in the optical response. So you can think of changing the refractive index by a large amount, or you can think of changing the actual geometry of the device. So I would say that using techniques like electro-optics, where you're talking about refractive index changes on the order of 10 to the minus 3 or so, it's that these techniques are not going to do much. But if you think of changing the overall geometry or changing um, the refractive index by some other means, that is definitely possible.
Great, thank you. We have two questions from Adam Erickson. Adam, you want to take the mic and ask the question? Maybe I will ask the question. So Adam is asking, are any startups working on bringing this to smartphones or small drones currently, also CubeSats?
Yeah, I know there are startups that are bringing this technology to smartphones or consumer electronics. I think some of the applications are for face recognition, so you can have devices that project some specific polarization and phase patterns, and based on the recorded uh, light, you can backtrack, for example, the face of a person. That's one application I know of. But definitely you can think of many other types of applications. I'm not very familiar with what all these startups do.
And his second question is also curious if this can be applied for secure spatial communications to protect against interference in contested environments.
I think so. I mean, you can basically think of sending the information by putting it through one of these devices that is uh, going to encode it in a very specific spatial mode, spatial and polarization mode. And maybe at the other end, you have like similar device that is configured such that it can decrypt what you're sending. So that is definitely something that could be done.
Okay. Uh, Another question from Chengling Su. Is two-photon lithography applicable to visible wavelength applications?
Um, I mean, in the sense that the resists are transparent, yes, you can apply it. However, uh, it, I would say that it doesn't really have the spatial resolution that we want. Um, so I would say that for some applications, you can probably be okay with this coarser spatial resolution. For example, we can push it down to let's say 500 nanometers. Actually, in some other also when you look at the resolution is different in different axes. So actually, I think for like lateral resolution is maybe closer to 200 to 300 nanometers, while vertical is a bit higher. Uh, so that's a bit large for most of the devices that we are designing, but it's possible that for some parameters or for some device responses that the resolution is sufficient. But yeah, in broad strokes, I would say that it would be nice to have larger resolution for visible wavelength devices.
And Adam is asking another question, which is a follow-up from the previous one. He's asking if the uh, 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 the interference in the contextual environments could be used for detecting the concealment systems. Uh,
Uh,
if- yeah, defeating concealment. I'm assuming it is to detect the concealment systems. Yeah, if there is a concealment system, if it is possible to do, we may figure that out.
Yeah, I mean it's not something that I work on,
Mm.
so probably Adam knows more than me in in this uh in this direction. But yeah, I mean at the end of the day, these are basically I say linear transformers that transform the wavefronts in all its degrees of freedom. So if that's useful for uh, defeating concealment systems, then yeah, these structures can be used for it.
Thank you, Andrea. I have one question, which is on the scattering part, on the pixel part that you are actually showing. So you showed there is 3D scattering of these. I mean, can these be utilized for some type of a detector?
Well, I mean, in some sense, like the image sensor
Yeah.
application is in some sort of sense of detector.
Yeah.
So, I mean, if you want to have a very specific response, I mean, but maybe you want to detect something that has like scattering at some certain wavelengths, for example, you can do that. You can engineer a system that is very well targeted towards um, sensing some very specific, say, wavelengths if you know what you're looking for. Or you can think of doing gas detection or maybe detecting some very specific polarization response.
Okay, but the system that you showed, they are more prone to the 3D scattering. Like, I mean, when it comes to the detection, we are talking about a competition between scattering versus absorption as well.
Um, yes, I mean, I guess yeah, you can employ it if whatever scattering you want to achieve is achievable by this. So I don't know if I think it's a very general framework, and I would say that generally yeah, you need to simulate it and see if it does what what you want it to do. It's a nuanced question because in sensing, right, you need to have a certain signal to noise, and you need to like say you need to balance scattering and absorption. So it's quite difficult to answer your question without knowing the exact parameters of what you want to do.
Thank you, Andre. Once again, I mean, let's thank Professor Farron. Andre, thank you so much. It was a great presentation.
You're
Uh,
welcome.
And next week, Amy is putting forward the seminar series for the next week. Next week, it is December 19th. Uh, Professor Blumenthal, Dan Blumenthal from UCSD, is going to give us a talk.
Okay.
Thank you all. Bye.
Thank you.